Welcome to this tutorial on using Desmos for polynomial functions to look for extrema, shade regions where it's increasing and decreasing, and even add a line where we can calculate rate of change with some movable points. I'll also talk about ways that we can enhance the graph along the way, making things more dynamic and more movable. But throughout this process, if you find that to be overwhelming, I will continue to come back to some very basic principles of just adding and labeling points. So stick with me. If you want to follow along, go to the description and open up the companion document where there's a link to the graph and then a list of the inputs that I put in to create these different features, as well as a transcript if you'd like to follow along that way. Let's dive right in. This first folder is our function definition, and in this one we almost have to stretch this way out to take a look. What we have is a polynomial function defined as a leading coefficient times each of its roots factored out. So the general form would be like x minus r1, x minus r2. My roots are -3, -2, 1, and 2. Some of these double negatives, they could be changed to positives, but I really wanted to keep it kind of with a framework design. And then that leading coefficient, we can solve for that very easily at x equals 0. So f of 0, when I plug in 0 for x, it's going to make all those x's zero out. The double negatives turn to positive, so I end up with 3 times 2 times -1 times 2. Now if I divide that over, I get my y value at x equals 0. In this case, we can see over on the right, that's 3. So what I really did here is I said I want a y value of 3. Now let's divide it by all those zeros. That's going to give me my a. This is a quick way to calculate a feature of a graph based on a bunch of inputs, much like we do with parabolic vertices, or the vertex of a quadratic function. We'll do -b over 2a using that standard form. So this will happen a lot. That's what we've got going on here. You can make the same type of graph pretty easily with very different inputs, just putting in each of your roots in those parentheses. Here I didn't have parentheses, so bear in mind you may have to add some in if you're going to change those to negatives. And then putting in your y value over all of those roots. Now there is a way to make this more dynamic. I can make each of these an r, maybe with a subscript, for example, like so. And I can also make that into a movable point. So this is r sub 1, f of r sub 1. Essentially saying let's have a movable root, and then let's find the function at that root to put it on the line, and that creates the dot on the line that also happens to be movable. So that's really fun and very interesting, and we can do the same thing with our y value too. So I'm not going to do all the roots. I'm curious if you could create a fully dynamic graph with a bunch of movable points, but I'll leave that to you. I would just say the other thing that can be really helpful or interesting is to set that y value as a movable point. Now I need to come down here and make a change because that first root became an r1 now. So I'll have to change that here, and now the 3 became a y0. And now I should, if I add in my y point, have a movable vertical point as well. Now this one occurs always at x equals 0. This is the y-intercept. So that would be 0 and y0 for my xy coordinates. Looks like something didn't work quite right because somehow this is flipped upside down. So let me think about this, and now I've debugged the problem. Each of these roots really needs a negative, and that's because if I go back up here, x is 0, that's a negative r1. Along this process, I make mistakes all the time. The important thing, look at the graph and make sure it works right. Now I've got one that I can move based on the y-intercept, and the first root is movable. Now it might become the second, third, or fourth. It is pretty fun to see what happens when those coincide. That becomes the same factor repeated or to a second power. So it's changing direction there as it goes through. Now here's one last thing that I find very interesting is just changing the degree of any of these. So if I change this to, let's call it nth degree, and add a slider for that. Now again, I got to remember to come down here every time I do that and make a change on this one. So that will also be affected. Now n is a power, so I want it to be 1 at minimum, and I want it to have a step of 1. And now I can see what happens. Now this is the power for the -2 root, so we got to watch that point specifically. Let's take a look here, and it's not framed great right now, but right now I've got a first power. It just goes straight through at a slight curve. It's not quite linear, but it goes straight through the point without any sudden curves. That's how I think of it. When we change it to a second power, that's a turning point. It's actually changing directions, just touching the graph at that 0. That would be the second power. And any even power will have a similar behavior. So 6th power, 8th power, all it is a sharper curve, a flatter 0, and then again a mirrored sharp curve. The even powers will go through every time. So 1, we went through the graph really without much curvature, without sudden curvature. With 3, we get this S curve as we go through. With 5, we get a maybe sharper S curve, and so on. Every even power will have that S curve with just a sharp edge, and it eventually almost becomes like a square as we move through that. So these are great ways to visualize some features of graphs and introduce a little bit of dynamic element to it that's very fun to work through. Now what I need to do is just dial all that back. If you want to keep it, you can, but I'm going to just hit undo until I go all the way back to before I put that movable root in there. And there we are. I just dialed it all back. And now we can talk about some of the other features that we had intended here. The next folder is one that I created for intercepts. All I really did was added a table. I put just x and f of x, kept it all black so it all matches. And then I put in, first of all, I have my 4 roots, and then right in the middle of that sequence is my 0 for x to give me the y-intercept. So we have each of the x-intercepts based on the roots, the y-intercept based on plugging in a 0. We can see all of those great. And it also actually helps me if I zoom out too much. This magnifying tool zooms it and fits it perfectly. That's why I like to include tables or intercepts or something like that in a table, just to have that automatic fit tool. We do not need to add regression. That is something more advanced to model data with an unknown pattern. Now, what I'd like to do is talk about the concepts of Extrema. Desmos gives us a great way to find those. It's actually built in. If I trace this, we will see dots come up for the Extrema. It would have also done that for intercepts as well. Now, the nice thing about this is if we click on one of those or look at that button to the right, we can export that point to the expression list. I love that tool. I think that's a great way to do it. So if you want to add a folder, we can organize this great, and we will call this Extrema. I'm going to put these Extrema into that folder. So I had it looks like an absolute min kind of down on the bottom left side. We've got a local max in the middle. It's making that purple, and then another absolute min over on the right side of the graph. Here it gave us approximations for the x value. There are other ways you can do this. If it didn't snap to that point, we see that it's snapping to points really well. We can also just type in a known y value. Let's say, for example, y equals 2, and that will give us solutions as well. These are approximate values because it's some kind of irrational that it's using some solving to get that. It's great for an approximation. When we really need an exact answer, we've got to work it out on paper. Just for pre-calc, solving this 4th degree is definitely a handful and not something that we look at in the homework. Now the next thing I might want to do is label these. We can add a label. It will just show that quantitative location, or I could call it absolute, min, or minimum. And you've got some options for where you put that label. You don't even necessarily need to have the dot, you can even just have the words there and have the position wherever you want it based on that set of options for the point. So you can do each of those points, any kind of labeling you want. I think for me, I will just take these labels off for the next part. The next thing I want to do is talk about the concept of rate of change. So the core concept that we first really look at is just, is it increasing or decreasing? And that's relating to the extrema. So it's going to be from left to right, kind of decreasing down to that minimum. Whether it's a local or absolute minimum, doesn't make a difference. We'll have a decreasing function to that point. Now I could define this as a x value like x1 or a and do a whole lot of things based on that defined value, but I noticed that the inputs just got really lengthy really quick. So I'm just going to use these approximations for this part. And I'm just going to observe that when x is to the left of that first root, we've got a shaded region where it's decreasing. I'm going to specifically label that with red, and I'll do increasing with blue. Now the next region is from that value. Copying and pasting works great here to the negative 0.5 was the next one, and with x in between, of course. And in this region, changing it to blue, we are increasing. Now I'll just do that process from left to right and just create this red-blue back and forth pattern. And the last one looks a little weird to me that way. I would probably write it as x greater than. Either way, it works out. But there's my red and blue back and forth. Like I said, I don't necessarily need my label for the minimum on that one. Now let's focus on how we could really convey what we just added to this graph. So I'd like to label these colors somehow and put in a note or a key that says red is decreasing, blue is increasing. I haven't really found an awesome way to do that. We can add a note to the input list, but what I've found works best for me is just putting in a point anywhere in that red region. So I can see here, for example, that at -4, -1, I'll be in that red region. And I can remove the dot but add a label. This is decreasing. And now make the color match. Even though there's no point, we've got a label on there and it's going to be based on the color that we pick. Now I've labeled the red region as decreasing. Pick any blue region. Maybe I'll just do a point that's even with that on the Y horizontal plane, but way over, let's go over to 3, -1. And that one is in an increasing region. I'll add that to the label and get rid of the dot, but make that match with the blue coloring. Now I've done a little bit of color coding. Of course, I could add all my maximum and minimum labels back in there as well. This is a great, helpful tool of labeling where you're adding a label without a point. I've done this to label different Desmos calculators I've made just to put a title on it, for example, in one of the corners. Now that's kind of a mess in there. I think I'm just gonna leave it and turn it off and get it out of the way. I'm sure that you've got a lot of customizing to do for whichever graph you're looking at. The last thing I want to talk about is average rate of change. So I'll make a folder for that. We can create a secant line or a line between at least a couple points on here pretty quickly just with function knowledge, knowing how to build equations. We're going to build the equation for a line in this case. And I've covered it really in depth actually in another video, but let's just do a really quick exercise. It does involve average rate of change. We need to talk about slope, but using function notation. So my average rate of change is going to be defined by a couple points. So let's define movable points, a, f of a. And I have done this in other videos. Then we'll go b, f of b. We can see the blue point worked great. Something didn't work. Oh, because A already has a meaning. Let's call it CF of C. Add a slider for that. Okay, so I've got my two movable points. You can use the classic x1, x2 if you want as well. I was worried that maybe you might have used x1, x2 already, so I went with something very different. Now here's my 2 points. Let's draw a line between them. To do that, I need to know their slope. Essentially, I need to build an equation that's like y minus y1 equals m times x minus x1. Now in this case, we'll pick one of the points to be our x1, y1, and that's either going to be the c f of c or the b f of b. Doesn't really matter actually either way. So let's make a little swap here. This will be my f of c to give me a y value at c, and this will be c right here. Well, the only other thing we need is an m to be able to pull that off. So my m is going to be a difference quotient, or a rate of change in y over change in x. So I'll have a f of c minus an f of b, that's change in y. So it's the output of the functions at those values, and c minus b on bottom. There you can see right there it actually filled in the equation, and now we've got it, our two movable points with a secant line in between. Now let's kind of expand on the concept I went through last time of adding a label. Suppose I wanted to add a label that puts the average rate of change next to this line. How would I do that? I kind of have to go off that same process I just did of having some kind of point. And we probably want it to be somewhat close to the line. For example, if I put that label way down on the bottom and I move my points, then might not be even close to it. You could put it right next to either of these existing points. That would probably be fine. You could say average, or let's go av rate of change equals, and then all I need is an m. And if we use the right coding, we can get it to paste that number. What we need is backticks. So I'm going to do a set of these backticks, a $, and then a set of braces within those backticks, and our m variable. So there we go. It's backtick, $, braces, m, braces, backtick. There's a little piece of coding that puts that label right on there. And now it's attached to the point on the right. I think that's just fine. It works great. There's also a way that we can put it in the midpoint or any other point on the line. For example, you could have it always on the y-intercept. There's a lot of options there. And I encourage you to dive into some of my other videos that have covered some of these other concepts. I definitely covered this secant line and average rate of change in a little bit more depth in a different video, and even truncated the ends of it so it only graphed a specific part of that just from the one point to the next. All those tools, when you start combining them in different ways, it can really be interesting to see how it works, and it also can help you really learn these concepts.